Alrighty. Hi everyone, TigerHawk-T3 here. Today we are going to look at Python's fractions module, which lets us work with potatoes. Fractions. Thought I would say something unexpected. The fractions module lets you work with fractions. How informative, right? Anyway, import fractions. Now what? This isn't nearly as long a module as I think decimal was. And by long, I mean how much stuff is there in the documentation. There are various ways to build a fraction. You can provide a numerator and a denominator. You can provide another fraction object. You can give it a floating point number, a float. You can give it a decimal object from the decimal library, from the decimal module, or a string that represents a fraction. So, let's look at those. If you give it a numerator and denominator, they have to both be rational numbers. If a denominator is 0, that's a 0 division error, because you can't do something divided by 0. This documentation spends a lot of time talking about how floats are not accurate, even though they may look precise. So 0.3, let's see if I can just, how about 40 of them, format, 0.3, it isn't actually 0.3, because it doesn't do that. Does this give us something else? Yeah, a little more than 0.3. So, because this is due to the floating point representation of 0.2 and 0.1, whereas this is the floating point representation of 0.3. Not all equivalent. So, if you fed 0.3, the floating point number 0.3, to the fraction constructor, you would actually have this plus, however many you needed. There's lots. Oh, it doesn't want to keep on going. Okay, fine. So let's make some fractions. Fractions.fraction. Let's first give it a numerator and denominator. Actually, let's give it nothing, because they have default values with a numerator of 0 and a denominator of 1. That's basically 0. And int does this too, and so does float. Isn't that cool? And string gives you an empty string. That's always cool. Let's do this. Fractions.fraction, and hello. And we get this. This means that this is a falsy value, so it behaves like 0 or the empty string or an empty list, etc. Fractions.fraction. Let's do this. That's better. Let's actually do this. Fraction of about 3 and 2 is 3 over 2. Fantastic. How about 1.5? Also 3 over 2. Now how about 0.3? It's not actually 3 over 10. Now let's try giving it, instead of a float, let's give it a string. Now we get 3 over 10 because it parsed, excuse me, it parsed 0.3 as something as a string. That doesn't give you any information. The actual number 0.3 is interpreted as a floating point value that is not actually mathematically 0.3. It's not exact. But when we give it the string 0.3, it says basically, well, there's nothing on the left, so it's smaller than 1, and there's something over here, and it sees how many places to the right of the decimal place it is, etc. And it actually looks at the string to figure out what it's supposed to be, and it says, okay, it looks like it's the decimal point is 1 place to the left of it, so it's this divided by 10, and so we have 3 over 10. Can we give it something with a slash? We can. How about 2 out of 10? That is 1 out of 5. My high school chemistry teacher would have disagreed. Not a great class. Not a great class. After a lot of complaining, my dad got fed up and said, okay, you know what? I will do a homework for you, and you will see that is how we do it. So he looked at one of my homework assignments and wrote all the answers on the board, showing work, everything. We had a big whiteboard, and I just copied everything down, just wrote it exactly how it appeared, and he got an F on that homework. He really wasn't happy that he got an F, because he has a bachelor's in physics and a bachelor's, master's, and PhD in mechanical engineering, and he knows what he's doing. He got an F. And then I'm like, now can I drop this class? And he's like, yeah, drop that class. Anyway, there are a bunch of examples in here with things we have already done. This ignores white space. If you do int of, let's say, 3, you get 3. You can also have a bunch of spaces. It'll still be 3. It automatically strips any leading or trailing white space. Sometimes you'll do a int of, you know, this dot strip. You don't have to do that because it already does. You can do negative numbers as well. Negative fractions, I mean. It recognizes scientific notation, so that's cool. That's good. $110, that's also good. This is good so far. Note that it's not guaranteed that we will do this. That we will have this correct result. How much was it not showing? Not very much. Okay, that's fine. Etc. and so forth. Looks good. So sometimes it works, sometimes it doesn't work. In the documentation's example, they do, 2.25. That works just fine. But how about 0.1? No. Does not work so great. You can give it a decimal if you want, whatever. You all know what a decimal is. You've seen that. You're experts now. Numerator, denominator. From float constructs a fraction representing the exact value of a float which must be a float. Beware that 0.3 is not f dot from float of 0.3, and it's that, because it's almost actual 0.3, but not quite, because binary representations of floating point numbers. Like this entire module is like, remember, numbers aren't what you think they are. Remember, don't forget. Did you forget? Don't do that. Like the whole thing, because it's kind of important. Maybe the first thing someone will do is, I'm gonna work with, you know, pennies and stuff, and nickels and dimes, and then they're gonna be wrong. So they want to make very sure that you know it's gonna be wrong. Because, let's just do 0.3, and we get 0.3, right? Looks fine. But if we do a fraction of 0.3, then it very immediately looks not fine. Very easy to tell that it's not actually 0.3, which is good, I think. So you can see not actually doing what you might think it was doing, and now you are aware, right? Instead of kind of lying to you. But generally, floating point numbers are okay if you don't need an exact value. That's why they're popular. Limit denominator finds and returns the closest fraction to self that has denominator at most max denominator, the past argument. This method is useful for finding rational approximations to a given floating point number. Oh. Let's do a fraction of 0.1 dot limit denominator of and the default value is 1 million. Okay. Let's say this should be 1 in 10. Let's give it a maximum denominator of 30. And we got a nice little approximation of 1 in 10. That's very handy. I like that. The example they gave was pi 15937, well, 6 something, but I'm going to round up to 7. And it's about 22 over 7, so that's great, because 7 times 3 is 21, and then 1/7 is 0.142856, 142856, and 1415 is pretty close to 1428. It's a reasonable approximation. There we go. Let's give it 100. 311 over 99. They the documentation's example uses a denominator limit of 1000, and they get 355 over 113. So that's pretty good. 22 over 7 is pretty close, I think. Alright. Alrighty. Recovering a rational number that's represented as a float. Goodness. Oh, you take the cosine of pi over 3. Remember, pi radians is 180 degrees, so a third of that is 60 degrees. So the cosine of a 60-degree angle should be half. But, of course, we can't represent pi exactly. So we have that nearly half. It's 4503, etc., divided by 900, etc. So 450 out of 900 with a few more digits afterward is very close to 0.5. But we do that and we limit the denominator, and since it's actually, let's do that. Let's import pi and cosine from the math module. which we have also looked at. F out of cosine of pi over 3. Not quite. How about just pi? Oh, is -1. So we wanna do this, and then we will limit the denominator to just the default value of 1,000,000, because notice how this is very long. So we have 3 digits and 6, and here are 9 digits. So this is much larger than 1,000,000. It's actually closer to here's 1,000, 4,000,000, 9,000,000,000, 7,000,000,000,000, 9,000,000,000,000. That's a big denominator. Let's limit it to 1,000,000 instead of 9,000,000,000,000. Let's do that. And then we get, 1 over 2. That's half. That's a very handy feature. I like that. And the rest, that's really not many at all. A fraction object has a numerator, and it has a denominator, 0 out of 1, because remember the default thing you get when just constructing a fraction with no arguments is that. From float, there's from decimal. We already looked at from float. Where is that? Somewhere. Did we do that? Fractions, etc. From float. Here we are. So there's from float, so we do that. There's also a from decimal, which expects a decimal instance instead of a float instance. That's I don't think you need to see that. Denominator. What else was there? I think that was all those. And next we have just magic methods. Magic methods, if you're not familiar with them, is a method name that starts and ends with 2 underscores. And methods like this with particular names, the one that I have here, for example, is REPR, the reproduction. And what those do is they are accessed by various parts of Python syntax, like one that you might be familiar with is init. You put this into your class definition, and whenever you create an instance of that class, like with this, is calling the init of that for that class, and returns an instance of that class. Your class can have I think there's an add, and that lets you define what happens if you do an instance of your class plus something else, generally another instance. So that's cool. There's a mul, which happens when you multiply it. So for this fraction, probably has a mul magic method that's it would look something like this. Actually, no, it would be that. So this is something that you might see inside this class, defined as a method in there. And self means this instance itself, and other is the other one, because when you multiply you have two things generally. It's a binary operation rather than a unary. And self is the one on the left, and other is one on the right. Like if you have A times B, it'll send A. It'll be something happening in the A object, and so self is A, and other will be B. So what we have there would be return fraction with self dot numerator times other dot numerator and do I have to do this? I don't know. I don't know if it'll get mad at me for mixing tabs and spaces, but we shall find out. Self dot denominator times other dot denominator, because that's how you do fractions, right? So that's great. That doesn't really do anything defined up here, but as part of class, this says, okay, when you have a fraction A times a fraction B, this sends, this works on the object A and looks in its mul magic method, because it knows that the multiplication operator should look for a method with this name, so that sends it to A, and self is then the A object itself. And that returns a new fraction, right, with this numerator times other, which is B over here, times that numerator, and the other argument to the fraction, right, is this denominator multiplied by the other one, because that's how you multiply fractions. So what do we have? We have a floor magic method, and it returns the greatest int, which is less than or equal to self, can be accessed through math.floor. Let's import some more stuff. Floor and seal. So how about floor of fraction 1.1 is 1, because the floor of 1.1 is, 1. So when we call the math.floor function, it will look up the floor magic method. Same for seal. Let's actually do technically you can do this if you really want to. Do integers have this? I don't know. Let's find out. Let's say 3 point, not point, right? It's dot mul. How about 5? That's 3 times 5. That's the same thing. So when you do, math.floor on a fraction object, it calls the floor magic method in that fraction object and does whatever it has to do to produce that result. Same thing for the mul magic method in an integer. But really, use this. That's the whole reason that someone wrote this. Notice how long this is? Notice how short that is? Yeah. Round as well can be accessed through the round function, and round is built in. This nothing you didn't expect. Right? This is bankers rounding, round to even in case of a tie. Good to remember. Fractions.gcd. This is not part of a class, huh? Okay. Greatest common denominator returns the greatest common divisor of the integers a and b. If one of them is non-zero, then the absolute value of GCD a comma b is the largest integer that divides both a and b. It has the same sign as b if b is non-zero, otherwise it takes the sign of a. GCD of 0 and 0 is 0. Deprecated since version 3.5. Use math.gcd instead, so they moved it to the math module. But I'm not using 3.5, so guess what? I can still do that. And it's deprecated, not removed. That means there's a better thing to do instead of this, so stop doing it. But I'm gonna do it anyway. I don't care. Fractions.gcd. How about 20 and 30 should be 10. Yes. How about if one of them is negative? Also 10. How about if this one is negative? Negative 10. That's what I said about. It has the same sign as b if b is non-zero. Otherwise, it takes the sign of a. So, b is non-zero, so it takes the sign of b. And here it's negative, so the answer is also negative. How about 0? This is just 20, I guess. And how about negative 20? Should be negative 20. Yeah. And now how about 0, 0, 0, as it says in the documentation. See also module numbers, the abstract base classes making up the numeric tower. Not part of this module. Just you might also be interested in short module. I like that, and has useful things. I like that too, and gives us results that we expect that are described in the documentation and that seem very useful, especially that maximum limit denominator. That's pretty cool. Define an approximation. I like that. So that's the stream for today. What will I do tomorrow? If I had to guess, I would say League of Legends. But it may be something else. Who knows? Not I. Probably League of Legends. Because, I don't know. Anyway, thanks for watching. What will the next module be? Random. It's going to be a random module next time. No, it's going to be the random module. There's a random module. I don't mean I'm going to pick a random one. I mean the random module. And that's what I'm going to have in a couple days after a gaming stream tomorrow. And other than that, I think we're good. Fractions, cool module. Good stuff. No surprises, if you noticed. I like that part. Because sometimes it's, like with decimal, or math was it? Getting the natural exponent of something and then the natural log back, and it doesn't give us, 1. It's like, that's great. Thank you for watching, and have a good one.